Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, hello, welcome to the session. I'm Frederick Tillman. I'm a seismologist working at the German Research Center for Geosciences in Potsdam, and I will be moderating the session today, where I will come to introducing Paul in a moment. We're all aware of attack on the Ukraine, and for some it's maybe a bit hard to concentrate on scientific topics at this moment, but unfortunately I fear the situation will stay with us for a long time. And I guess one of the aims of AI for Good is to promote the free exchange of ideas, which is very important, and how to use the methods of artificial intelligence to relieve suffering and maybe even bring joy. And so this is certainly something we need to continue to pursue. In this context, I'm very glad to welcome Paul Johnson, whose research already has impact on understanding earthquake physics and seismic hazards, and who will talk about a very exciting line of research with great potential for improving our understanding of earthquake preparatory phases. Paul works at the Los Alamos National Lab in New Mexico, where he spent his whole career, starting in 1984, directly following his master's at the University of Arizona in Tucson. He was doing research straight away and continued and was happy with that for some time, and then unusually started his PhD in physical acoustics nearly 10 years after starting in research. He did his PhD at the Sorbonne and completed that in 1998, then returning to Los Alamos, where I think he was also employed in the meantime. Paul is a true polymath with outstanding contributions in a range of different fields, among them the physics of faulting and fracturing, nonlinear elastic behavior, and the methods of time reversal in acoustics and geophysics. In this, he's drawing on experiments carried out in Los Alamos, but also with collaborators in Rome and at Penn State to explore nonlinearity and friction in a controlled environment. And this gave rich insights into both earthquake-like related failure processes and the build-up to them, and the nonlinear behavior of earth materials. Here he puts a spotlight on the mesoscopic scale, which sits in between the large continuum mechanics view that we seismologists are familiar with and the very small crystallographic view, dealing with a messy part in between that others shy away from. And this is but very important for granular and composite material behavior, both engineered and natural. If this was not enough, Paul's lab was then also at the very forefront of what I would call the new wave in artificial intelligence in seismology, with a paper in 2018 on predicting the timing of laboratory earthquakes, which really alerted myself and also many others in the community to the potential of machine learning techniques, or the potential of machine learning techniques for knowledge discovery. Of course, since then, AI methods have truly exploded in the geosciences and seismology in particular, and a lot of progress has been achieved, such that it's really hard to believe that it's only been 4 years since this paper came out. But what really impresses me about the approach of Paul and his co-workers is the focus of using AI not just for prediction or pattern recognition, the standard ways, but for aiding the process of physical discovery and understanding what is really going on. Pursuing such different lines as Paul does is great for making connections and for coming up with new views based on the bigger picture. But it's normally then really hard to be at the forefront in the subdisciplines. But this has not been a problem for Paul. He's a fellow not only of the Los Alamos National Lab, but actually 5 different societies in geophysics, American Geophysical Union, physics, acoustics, and nonlinear material sciences. And each of these fellowships alone would present a great honor and a real achievement. So this is truly impressive. And finally, before we hand over to Paul, remember how I said Paul is a polymath? In line with the tradition also of many great minds, Paul is not only a hugely successful scientist, but also a renowned artist. And of course, Santa Fe is just the right place to be if you're into art. And I can see that there are many exhibitions in Santa Fe and Denver where his work was shown. You can see also some of that on the web, and his mastery of pastel colors, which he seems to be fond of. But today, of course, the focus is not on that, but on what AI can tell us about earthquakes in the lab and in nature. And yeah, with that, I would almost hand over to Paul. Let me just remind you that you can ask questions in the chat, and I will read them out later, and we will look into that. So over to you, Paul, now. You can share your screen now and start.
Okay, can you hear me, Frederic?
Yeah, we hear you well.
Can you see the screen?
We see the Zoom window now, so you have to put the PowerPoint on top. Yeah.
Okay, so you see the PowerPoint?
Yeah, we see the PowerPoint now. Now we see actually a full screen. So
okay.
You might try going into presentation mode. Maybe that works this time.
Let's try presentation mode and see. How does that look?
Yeah, now it works. Fantastic.
So thank you so much, Frederic, and please interrupt me if there's an issue with the presentation since I won't see it. Very kind introduction. I really appreciate the introduction. I really appreciate the opportunity to speak to this community. It's an incredibly exciting time to be in AI, in science, in every domain. We're seeing remarkable changes so rapidly it makes your head spin. In today's presentation, I want to talk about our work on earthquake faults. We start with laboratory simulations, and I also discuss some applications to earthquake faults themselves. I have a large number of collaborators, both at Los Alamos and elsewhere. You see a list of some of them here, but certainly not all of them. I appreciate my collaborations with all these individuals very much, and many of them are really doing the hands-on, day-to-day work with machine learning. So I'm going to the next slide. Do you see the next slide, Frederic?
Yes, that's good.
Okay. So as I say, there'll be a brief introduction to tectonics and earthquakes. So I hope I don't offend any of the geoscientists online. This is for individuals who really don't have any background in geoscience. And then I'll have a brief introduction to AI, but you're seeing a lot of that in these presentations, so I won't dwell. But I'll be specific to our applications. And our applications then will be of probing faults and slips with machine learning. At that point, I'll conclude. So first, I want to start with this really fun video of tectonics. So bear with me and please listen. You'll hear a different voice here, but please listen.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So I hope you enjoyed that. This is really the engine behind everything we see in geoscience. It's mantle convection that drives the plate movements, that causes faults on the larger scale, and that creates volcanoes, etc. So this will be sort of the framework from which we're working in. So here you see the what's known as the ring of fire. These are primarily subduction zones in the Pacific, and you see subducting plates beneath North America, Eurasia, etc. And you see many earthquakes, large earthquakes. The biggest earthquakes in the world take place in these subduction zones, the magnitude 9s you read and hear about and maybe you have experienced. And also the red dots are showing you volcanoes. So we have a massive number of volcanoes associated primarily with subduction as well. I will go ahead and skip this. It's another video, but we probably don't need to see that. Also, because of the nature and the complexity of the Earth's crust, we find that we have not just these subducting plates, one going beneath the other, but we also, due to the stresses imparted by the convection currents and the plates being created in the oceans primarily, we see stresses on the Earth's crust that produce other kinds of faulting. Here you see a strike-slip fault, known as a strike-slip fault, which is a vertically oriented fault. This one in China. Very nice aerial view. Here we have another strike-slip fault, or transform fault as they're called for the geoscientists. And what we're going to see is a simulation of fault in action, and we're going to see the waves propagating outwards from the fault as the fault propagates, and see the impact on the Los Angeles basin in California. So here we go. So you can see the initiation of the fault. You see the surface waves propagating outward as the fault ruptures to the northwest, and watch the waves as they propagate into the Los Angeles region. You see that you get large density, which is associated with larger amplitudes of these waves. There's sort of a ringing of the soft sediments in these areas where you have soft sediments associated with a fault. And it's those regions which are really dangerous because you get amplification, wave amplification of the surface waves, which can lead to the damage we all are aware of. I just wanted to show you a little bit, if you haven't ever experienced an earthquake, it's truly frightening. And I wanted to show you just a video of a video taken by an individual in Japan from the 2011 magnitude 9 earthquake. And I'll just show you a bit of it just to get a sense of what it's like for individuals experiencing it. Note here the differential movement you're going to see right in front of your eyes. And the fountain. And then you see fountaining of water. This is something like liquefaction. Some of these could be broken water mains, but primarily this is something like liquefaction. But I hope you saw the differential movement in that sidewalk. It was truly remarkable, several centimeters of differential movement. We'll continue just a little bit and then we'll proceed. So you could see additional fountaining taking place, etc. So this was a very large earthquake and truly a frightening experience for all involved. So let's move on. So that's just a little bit of an introduction to tectonics and earthquakes. I know it's brief, but I hope it was helpful. Now we'll move into AI with a little bit of background and go directly to our applications for earth sciences in faulting. So to start with, the goal of machine learning is to learn from data to make accurate outcome predictions without being explicitly programmed. And it's allowed the kinds of advancements we're seeing across all of science and other domains. In classical science, I'll call it now, where we're not using machine learning, we have a domain expert you see. I don't know if you can see my mouse, but in the upper left, we have a domain expert lens we look through, and we have a hypothesis, we collect data, we analyze data that we have collected, to answer whether or not our hypothesis was correct. And we work with an intrinsic bias simply because we have a working hypothesis. It may be right or wrong. It may be that our working hypothesis is entirely wrong and we have no idea about it. So we come up with some answer, and the answer may be no, we don't make a connection between these data and whatever we're looking for, but it might be there. It might be there. It's just that we couldn't find it. And that's the beauty of machine learning. With machine learning, we have essentially an unbiased view of the data. Yes, we're in a supervised learning approach. We're posing a question whether or not the data maps to some variable, and we'll get into that briefly in a moment. But it's really an agnostic mapping of automatically extracted features from data to variable or data structure. So the machine learning model does all the work for you once it's trained, and it allows a view into the data that we've never seen before. And we're looking at features of the data that we never thought possibly had any impact on the question we were trying to answer. So it's a remarkable difference between the classical approach we all learned as scientists and what we're doing today with machine learning. This, by the way, is from a review paper written just a couple of years ago and published in Science. So AI has been around a long time. Most of you know that. In fact, preceding the 1950s, for several decades, there was plenty of work in mathematics and computer science leading up to the 50s when the term was coined, AI was coined. Then in the 80s, starting at about the 80s, we had machine learning come on board, a type of artificial intelligence. In fact, machine learning is the path to artificial intelligence, in my perspective. And then deep learning came on board in about a decade or so ago, and deep learning has changed everything. It's deep learning that allows this agnostic exploration of data to answer questions we had never realized possible. So there are several categories of machine learning. There's supervised machine learning, there's unsupervised machine learning, and reinforcement learning. So supervised is often posed as a regression problem where it's task-driven, you're trying to predict a value. Unsupervised is let the data tell us what's in it. It could be clustering or something like that, clustering of the data or something like that. Reinforcement learning is let's learn from our mistakes. So these are the three general categories people tend to break machine learning into. There's a rule of thumb that you only use machine learning when, excuse me, did you just lose the screen?
Yes, we did. So we see the Zoom.
Do you see it now?
Yeah, it's back.
Okay, so excuse me. So the rule of thumb is that you only use machine learning when traditional programming methods are not effective or feasible for solving a particular problem. So you don't throw machine learning at just any problem. If you can solve the problem by doing a simple regression or taking a Fourier transform to look at spectral content or what have you, then you don't bother with machine learning. It's when you're trying to answer a problem that's quite complex that you've been unable to solve in any other way. So this is a really fun book. People worry that computers will get too smart and take over the world. But the real problem is they're too stupid and they've already taken over the world. And I think many of us experience this on a daily basis, right? You call your doctor's office, you call some business, and you get put on hold and you go through some infinite menu that's computer driven, and you never get to talk to an individual. This is an example of how maddening our world can be with computers. On the other hand, it opens up analysis approaches that we'd never hoped we could imagine before. So this is an actual surface of a fault measured by a colleague of ours, Emily Brodsky at Santa Cruz. And you can see the surface of the fault. You can see a scale there of 1.5 meters. And you can see there's a roughness of the fault. There's low frequency undulations, long period undulations, and higher frequency content as well. It turns out that from what we know, this is a fractal geometry, or self-similar, meaning that at all scales you have this kind of roughness. And so what it does is create a complexity in faults that makes them very challenging to understand, especially since they're in the subsurface, they're opaque, we cannot see them. So they're very difficult to unravel. The physics of fault is a very challenging problem, and therefore earthquake prediction is a very challenging problem. How do we capture the controlling physics of such a complex system? Can new data analysis approaches help? This is the question we were asking ourselves a decade ago. And about 5 or 6, maybe 7 years ago now, colleagues of mine at Los Alamos pointed us toward machine learning and said, why don't you try this? And not knowing essentially anything about AI and machine learning, we dove in, and what I'm going to show you today is the evolution of what we've learned. So how do earthquakes evolve? So we're going to use data-driven approaches. These are primarily regression approaches, and the answers we seek are hidden in existing data. So the question we're asking ourselves, in fact, is we're using specifically what I'm going to show you today is use of seismic data. So in that bottom left panel, you see a first P wave, a compressional wave, then you see the first S wave, and then you see the surface waves. So these are classically what are used to understand geoscience in general, to probe faults, used for tomography, used for all sorts of applications. The question we're asking is there information contained in that signal preceding the P wave and following the surface wave that we've just missed in the past? And the answer is yes, and that's what I'm going to show you today. So here's the quick summary of our work to date. So we're using a variety of data sets. I'm going to focus on the seismic data sets. We're also using GPS, and I'm going to talk about that a little bit, and INSAR, although I won't discuss INSAR, which is interferometric synthetic aperture radar. GPS and INSAR measure surface displacements on the Earth. We're also using simulations. You can see in the bottom right-hand corner. Next to that, we're seeing those are computer simulations. We're also using laboratory experiments, and we're also using Earth data. So I'll talk about some of these as we go forward. So just as a brief introduction to supervised learning, this is it in a nutshell. So basically what one does is you take an input signal, in this case it's a seismic wave or acoustical wave, and you see if you can learn a mapping between that signal and some property on the fault in this case. And you frame that in the form of a regression. And you build that connection, that map, with a machine learning algorithm. So the mapping is the machine learning algorithm, f of x. And you build that in a training procedure. Then you do some validations of that model to make sure you believe what's coming out of it. Then you test it on data it's never seen before. So that's the general approach, supervised learning, in the form that we're using it. And you do this using features. You don't directly use this signal. The model extracts features from the seismic or acoustical data in this case. Could be any data set, but seismic data or acoustical data in this case. And it's using those features. It could be spectral features, that is frequency space features. It could be amplitude or magnitude features, any number of things, the moments, all sorts of different features, hundreds of them potentially, that the model will use to see if it can make this mapping. So that's the basis of what I'm going to show you next. So with that idea in mind, what you see in the top left-hand panel is you see this is strain on the y-axis. This is dynamic strain. So just think of this as an amplitude as a function of experimental runtime in this case. And on the bottom, you see measured shear stress on a device I'm about to show you. And this is a laboratory earthquake. This is a laboratory earthquake. And this is what is known as the inter-event time. And we're trying to see if we can learn a mapping between some time window of this acoustical signal and the shear stress or friction on the fault. The actual experiment off to the right is, let me describe that briefly. What you see is a 3-block system. You drive that center block down at some constant velocity while holding the 3 blocks in place with a normal load, and it begins to stick slip. And just above it, you see the pink or red signal, and you see a sequence of these drops in tau, which is the shear stress, as a function of time. And each of those drops is a laboratory quake. There's a granular gouge between the 3 blocks. So that represents granular gouge that you would have in a fault zone, or is meant to represent that. So again, we're trying to see if a machine learning model can learn this mapping between the time series signal, the acoustic emission signal, and in this case, the shear stress or the friction on the fault. The bulk friction, by the way, is just the shear stress divided by the normal load, for those of you who are interested. So here is a training and testing input and label or target data set. So on the left-hand side, you see the acoustical signal, and the green is the training input to train the model. Each one of those impulses you see, those large deviations from 0, are a burst associated with an earthquake in the laboratory. On the right-hand side, the green is showing you the associated shear stress on the fault that you're measuring on the device. So you're using that information to train the model, features from this input data set, trying to predict instantaneous behavior of the shear stress. And you're using a time window analysis. So you're moving a time window through that time series data and trying to map to successive points in shear stress space. Once you've trained it, you go to data the model has never seen before, and that's the sort of lavender color, and you're trying to predict the testing of data it's never seen before. So that's the general approach. I hope that's clear. So here's an example. Again, we're showing the experimental runtime on the left-hand side. Now, this is just the testing data. So this is the portion I showed you on the right-hand side in the previous signal. So we're looking at the acoustic data amplitude in arbitrary units on the left-hand side as a function of experimental runtime on the x-axis. And on the right-hand plot, you're looking at shear stress on the y-axis as a function of experimental runtime. And you see one of these tiny moving windows where you're trying to take features of that acoustical signal and predict the shear stress on the fault. And on the right-hand side, you're looking at the actual measured data on the device, I'll call it the earthquake machine that I showed you 2 figures ago. And that is the red dashed line. You can sort of make it out in the background, whereas blue is the prediction. So the blue came only from the acoustical signal here via the machine learning model. So the blue is the prediction. The red, which it overlays very well on top of, is the actual measured data. So when we first saw this, it was absolutely remarkable because it told us there was information contained in the acoustic emission signal at all times regarding the state of the shear stress on the fault. We had no idea that was the case previous to that. So we were truly astonished at the outcome of this first analysis. So I hope that's clear. This is probably one of the most remarkable things I've seen in my career in terms of especially in terms of related to fault physics. So just to reiterate, the continuous signal contains a fingerprint of the instantaneous behavior of the fault at all times for the laboratory studies. We could also predict the time to failure. So if you look at the top left signal, you see the shear stress as a function of time and the time to failure. The time to failure is this red dashed line, and it's simply based on this top figure. It's the time it takes from the previous failure or earthquake to the next earthquake. So you're counting down on the y-axis the time to the next failure. And you're trying to use another machine learning model to make that prediction using the same data sets. So you're trying to do earthquake prediction, at least of the timing of an earthquake. Here again, you see the prediction. I'm not showing you the intermediate steps. The blue is the prediction. The red is measured on the device. The model never saw the red. It only saw that during training from a different data set. So you can see that as soon as you have an earthquake, it's predicting the time of the next one. And it does a better and better job as you approach the failure. So this too was truly remarkable because it said there was information contained in this acoustic emission signal about the future behavior, which is to say the next failure event. The reason is that the signal, the acoustic emission signal that I'm not showing here, but I am showing on the right-hand side, this acoustic emission signal again in the top panel. It contains information in terms of statistical characteristics, the features that I mentioned earlier, in particular the variance of this signal, the kurtosis, and the threshold. And you can see that they evolve through the slip cycle. So again, the large bursts are associated with earthquakes in the laboratory, but you can see the variance increases, then drops immediately at the time of an earthquake, etc. And that's why the machine learning model worked. It found these statistics. If we had known about these statistics, we did not need machine learning, but it took machine learning to tell us about them. So following this work, we sponsored, with the help of Department of Energy and other collaborators, a Kaggle competition that was held and ended about 3 years ago. And that we had, you can see here, 4,500 teams approximately. There was prize money, so there was great motivation. And following that, we published a paper on the outcome of that in Proceedings of the National Academy. So you can see that as well. So now the question was, what about Earth? And I see I've got just about 15 minutes or a little less. So that's about right for what I want to show you. So we're going to talk about episodic slow slip and tremor in Cascadia. Cascadia is the northwestern US, Washington State, and also Canada, the Vancouver area. So here's the idea. Remember in that movie I showed, you saw subduction. And here you see the Juan de Fuca plate subducting beneath the North American plate. And we have a region where we have slow slip and tremor, and that's what we're going to focus on here. And I'll tell you why in just a moment. Megathrust earthquakes take place in this locked zone. So again, the big magnitude 9 events you hear about take place here. But there is also activity down the fault from where the locked zone is, where it's continually slowly slipping. And that's what we're going to focus on here in the next portion of this presentation. So this is a map of Victoria and Seattle area. This is Victoria Island. And these numbers are associated with seismic stations. On the right-hand side, you can see seismic signals recorded from those. And we're using data sets that you're looking at, for example, on Vancouver Island, a number of these seismic stations. And we're using GPS as our label or target. GPS measured displacement or displacement rate. So this is a famous figure from Rogers and Draeger from Science in 2003, when this idea of slow slip associated with something called earth tremor or non-volcanic tremor was first really described in detail. And so what you see is displacement on the left-hand y-axis, time on the bottom, and on the right-hand y-axis you see tremor activity. Those are the bursts you see on the bottom axis. And you can see that we see displacement continually taking place. Then there's a slow slip event where there's a slow slip that takes place on that portion of the fault I mentioned in ways I won't go into details because I don't have time, but it repeats. And you can see it repeats on the order of every 13 or 14 months. And that's really important because for supervised machine learning, we need a training set sufficiently large to train a model, and then a sufficiently large data set to test the model. The problem with earthquakes in general is you have time frames of decades to hundreds to even 1,000 years between earthquake events. Here, our slow slip events take place every 13 or 14 months. So we have data back to about 2 decades, 3 decades now, that we can train and test on. This is why we're using slow slip. And this is why we went to this data set. Okay, so I won't go into details. This is a convolutional neural network. I don't really have time to go into the details. Happy to talk about that if there are questions. Our model input are continuous seismic data, in this case, measured at the Earth's surface. In the laboratory, they were acoustic emission data measured on the side of the apparatus. The model out and the model output are displacement rate, in this case, measured with global positioning satellite, GPS. On the laboratory device, it was displacement measured on the actual fault. The models we're using in this case are XGBoost, and we're also using deep learning, autoencoder primarily, but also CNN. Okay, so I'm going straight to the result. So the same approach, right? We're using seismic data as input. We're trying to predict the instantaneous displacement rate on the fault, and we're going to see how we do. So on the left-hand axis, you see the displacement rate in millimeters per day measured by GPS on the Earth's surface, and you're assuming there's a coupling from the fault to the Earth's surface through the elasticity of the plate. That's the assumption. Then you're looking at calendar date on the bottom from a little before, about 2011 to just after 2017. In this region of crosshatched region, we have data missing. That's why there are no data there. So the red line is the actual surface displacement rate measured from one of the GPS stations on Vancouver Island. The blue is the predicted displacement rate. And you can see the model does a remarkably good job at predicting the instantaneous displacement rate on the slowly slipping fault at all times. Again, this was truly remarkable because we took conceptually the ideas we had developed in the laboratory, applied them to slow slip and Earth, and it worked. Again, it was basically an epiphany, and we were just marveling at the result, the power of machine learning. So in this case, the most important statistic was the interquantile range. And I think in short, it's another energy related statistic, just as they were in the laboratory. I don't know that I mentioned that, but all of the statistics that were important, or the features that were important in the laboratory, were energy related. So you're looking at calendar time on the x-axis, and on the y-axis, you're looking at displacement rate. But now you're only looking at one of the features that was identified by the model and used. And the red is the actual, the red is the quantile range, and the black is a prediction. So we can forecast failure time just as we did in the laboratory. And what we see here in the bottom right-hand figure is the time to failure. That's the red dashed line. Remember, again, it's just a countdown. So the y-axis shows you a countdown in days from the previous event to the next event. And you see that repeatedly. And the blue is the prediction, the machine learning estimates of time to failure that the model shows us. So again, we could predict the time to failure. This isn't true earthquake prediction because you need also magnitude and you need location, but timing was actually working quite well. Another big surprise to us. I guess I won't go into the details here because I don't really have time. I'll say there are parallels between the Earth and the laboratory in terms of the slow slip observed in Cascadia and slowly slipping faults in the laboratory. And just to reiterate that it's the features that the machine learning models identified were energy related. I think that's really the important aspect of the slide. So I'll continue. So I'll spend the last couple of minutes talking about attacking the challenging problem in Earth. So I just showed you results in Earth from slowly slipping faults in Cascadia. We've also looked at slow slip in Japan and South America and Mexico, etc. But also we're really most interested right now in seismogenic faults, the ones that cause the big earthquakes. And as I mentioned, you're looking at time scales that are so long, they're prohibitively long for training a data set. So we tried to apply some of these techniques to seismogenic fault on the San Andreas fault in California at Parkfield. Some of you are familiar with that. And it worked modestly well, but not as well as we had hoped. So we went back to the drawing board and we decided to return to the laboratory and use fault simulations and laboratory data. So to start with, we simulate the fault with numerical simulations using a finite element plus discrete element approach, and we try to predict the behavior on the fault. And then we make another step that I'm going to talk about here. Once the model has been trained, we take a portion of the laboratory data, retraining the latent space of the model only using laboratory data, just as we would do in Earth. So we're using a numerical simulation, we're training the model, we're testing that model. Now we retrain the model further by only training the latent space with data from the laboratory experiment with an eye on Earth. And I'll come back to that in just a second. Again, I'm not going to go into the model details. It's an encoder-decoder model. And the model input and data sets, same here. We're in the simulation. We're using something that's akin to acoustic emission. It's actually the kinetic energy coming out of the numerical simulation. Here's the friction coefficient, which remember is the shear stress divided by the normal load. And here is the laboratory data, the normalized acoustic emission in the top, and the bottom is the friction coefficient. So what we're trying ultimately to do is to predict, using the kinetic energy out of the simulation, try to predict the friction coefficient on the fault. Here you see that. So this is trained on the simulations and you're predicting the laboratory fault behavior. Just look at the top panel, panel A. You can see that the black is the measured values on the experiment that the model has never seen, because this is the testing portion of the data set. And the red is the prediction. You can see it does a pretty good job trained on the simulation and predicting the laboratory behavior. Surprisingly good job. You can see that in the MAPE. So then the next step is with an eye on Earth. And this is the last thing I'll show Frederic before wrapping up. What you see here is now with an eye on Earth, where we have only a portion of a slip cycle to train on, because the time between events is so large, we use a portion of the event, say the here's an earthquake in the laboratory, this is, time, and the AE amplitude and the friction coefficient. So the blue is the friction, the red is the acoustic emission. So we have a laboratory quake, we have this increase in the friction, a small failure beyond that, and then the major earthquake following that at the end, you see on the right-hand side. And so we train only on this pre-failure portion using the retraining of the latent space. And again, we would do that because it's exactly what we want to do in Earth. We want to develop simulations for an Earth fault, and then use a bit of the data from the fault to additionally train the model. And what we see, and you can see this look at the bottom, the green figure, you can see the prediction is in red, and in black is the actual measured value on the fault, which the model does not see during testing. And you can see it does a pretty good job. It doesn't capture the full frictional failure. Mu is the friction, by the way. But it does a pretty good job in capturing the event itself and the increase in the shear stress, the friction through the slip cycle. So we were pleased with this result, knowing we could do better. I won't go into details about the post the pre-failure versus the post-failure, but the post-failure was the most successful, the portion we used here in green. And time to failure, once again, that worked reasonably well, not as well as just using the laboratory data to predict laboratory acoustic emission, but using the simulation with this cross-training of the latent space, as we'll call it, does a reasonably good job. So it gives us hope that this is a path forward. So this is the second to last slide. We have a two-pronged approach to seismogenic faults in Earth, which is to train on simulations of Earth faults and test on actual faults using seismic data as input and surface displacement as target. And then we would additionally train that model, cross-train that model with data from the fault itself, some small portion of the data set, small portion of a slip cycle, as it's called. Then another approach we're using is to use a frictional model in the deep learning model with the same input and target. And this is physics of informed machine learning, which you're hearing a lot of buzz about today, where you include the physics of the behavior you're interested in and try to predict. So these are the approaches we're currently using. So in summary, the take-home message is, what we see is what we thought was noise coming out of the laboratory system and in Earth. We found out the noise is the signal giving us the insight into the fault physics. It's the most important signal in the system, in fact, and it took machine learning tools to reveal it. Thank you very much for your attention.
Yeah, thank you very much for this great talk. That really was a sort of tour de force from the lab into the field. Great to see all of that. So I got some kind of fairly general questions at first that I guess maybe relate first to the first part of the talk. If there's generally a higher frequency of earthquakes related to climate change, for example, the loss of ice sheets in Greenland.
Is that a question?
Yeah, it's a question.
Yeah, I think the geoscientists that are listening know this is the case, that as you're unloading, if you're in regions that are earthquake prone, you definitely see more fault activity. And it makes sense, right? Because as you change stresses in a region, you might induce faulting. And in this case, you're releasing stress on fault. So you might well see increase in seismicity.
Okay, thank you. And also another general question on the coupling between atmosphere and ionosphere. And I'm not sure you know about this. I will ask about it anyway. Yeah, so there's a few studies also show that an influence of plate tectonics and mantle convection on the Earth's magnetic field seems possible. Yeah,
right.
Do you see like a coupling there?
Right. So this is an interesting question, and I certainly don't. I don't know much about it. I've heard the same thing, that there could be this kind of coupling. The dynamo of the Earth certainly couples to the ionosphere, and so it's quite possible. And so that's. I'm sorry to say I can't really say more. And there are people that are studying this problem, so I apologize that I can't say more about the topic.
So maybe I also have a question that relates to your kind of this transfer learning approach from the DEM model to the lab results. I mean, or generally in the lab, the failures seem to be quite regular.
Right.
So in a way, if you take some kind of very cheap predictor that just says, you know, you're gonna have the next earthquake in the median time of these failures, you probably also do fairly well. So I think there are two questions related to that. One is, sometimes one does see some irregularity, and I was wondering what introduces the irregularity. And B, if you have sort of scored your machine learning algorithm against maybe somewhat more naive algorithms, and to see what the information gain is there.
So this is a really interesting question, and it's something that lots of people ask. You see this very relatively regular behavior of the laboratory earthquake, so why not just predict on the mean or median value of the inter-event time? If you do that, you do much worse than you do with machine learning model. And the reason is because you're averaging a signal that looks periodic, but it isn't that periodic. It slips on, at the same time within 50% error or something like that, approximately, depending on the experiment. But the reason the machine learning model works so well is that it identifies features, energy features, and you can see again the variance, the kurtosis, the threshold of that acoustic emission signal. Again, the bursts in amplitude are associated with the laboratory earthquakes. So you can see that evolution in those energy features, which is why the model was so successful in making instantaneous and future predictions of the shear stress and the time to failure. If you train a machine learning model just on the inter-event time, again, you do far worse. You do approximately the same you do with a mean or a median, as you would expect. So, Frederick, I'm not sure I answered your question, but please ask again if I did not.
I think you answered the part that it does better and that you really compared this. I was wondering what causes the irregularity.
Oh, the irregularity. Yeah, that's a really good question. There's an instability in the fault gouge that that depends on temperature, humidity in particular, and also with the gouge thickness. So on different days when the humidity is different, you might see less or more irregularity for reasons that must be associated with contact forces in the bead pack. But as you go further along in an experiment, things get more and more irregular too, as there's a thinning of the gouge, because as an experiment proceeds, a fault gouge is pushed out of the bottom of the device, and so the layers become thinner and thinner. And as the layers thin, there is this irregularity. So you get what is known as stable sliding for long periods of time, then you'll have a failure event, and then you'll have stable sliding for some unknown period of time and a failure event. So those regions are highly aperiodic, but you can also do a reasonably good job in predicting their failures as well. So I don't know if that answers your question, but that's kind of the short version, and there's much more detail associated with that.
Yeah, I guess it always is. And maybe if I may ask another question, as people
Please.
are maybe formulating here more. So the systems you looked at, which I think is completely wise, are relatively simple in that there's sort of one large fault that is dominating, and they seem to show a fairly regular behavior. I mean, you just talked about the conditions that it's irregular, which is also true for the Cascadia event. So in real Earth, we often have interacting faults. And of course, as soon as you've got two systems interacting, things become a lot more difficult. Or maybe even if you have a megathrust fault in the subduction zone, you might have different segments that are interacting, where again, Cascadia might be a kind of simple end member model. Do you have any ambitions to look at those interacting systems, and what are maybe your approaches?
Yeah, I mean, you bring up a really important question, Frederic. Certainly that's the end, not the end goal, but that's a major step that we'll take as we move forward to faults in Earth. The first is to try to isolate portions of fault that are apparently not interacting, if that's possible. And then eventually you're going to deal with interacting faults. So you'd have to be using simulations of interacting faults. As you're probably aware, there are a number of simulations out there where people are attempting to do this. The Southern California Earthquake Center, for example, is developing such an approach, and the USGS is doing the same in the United States. So that will be an important step along the way. Our first step, though, will be, can we take a portion of a fault that may not be interacting with others, such as the Parkfield section of the San Andreas fault, and predict some of the fault characteristics using acoustic emission or other geophysical data. Does that make sense?
Yeah, sure. I think that is clear. I'm not sure to what extent the Parkfield fault is non-interacting, but I guess you're right compared to some other more complicated systems.
Right, compared to some others.
System.
Yeah.
And I guess it's a nice example of its regularity and then irregularity from the prediction experiment.
Right.
Okay, so I've just got another question here through the chat, which is also somewhat technical. Is how do you choose the time window and what is the interval you decided to use? And I guess that refers to both the laboratory ones or the Cascadia ones also.
Well, the short answer is hyperparameter tuning. You know, you go through a tuning procedure, as many people who are listening know, of a model, which is very time consuming. And what you try to do is optimize the result on the target or label. And you do so by changing, for example, the window size on the acoustic emission or seismic data, the overlap, whether you're overlapping or not. These kinds of tuning parameters are an important step in optimizing the answer. So as many of you know, a model just doesn't just work this first time you try it. You have to go through this procedure where you're playing with these parameters that affect the model and the output of the model. And the time window and the window overlap are really important aspects of that. So that's the short answer to the question. I hope that answers the question.
Yes, maybe what does the outcome? I don't know if you remember that. Obviously, that these are these numbers. Maybe in terms of percentage of a typical cycle or something.
Yeah, I think in most of the lab results I was showing you, and I think you can see it here. See, this is actually one of the windows. This is from a paper that Bertrand Rouet-Leduc and we published in 2018 in Geophysical Research Letters. So that's the acoustic emission amplitude on the left, experimental runtime on the x-axis. And you can see the relatively narrow time window, which looks to be, in this case, about approximately a couple seconds. And we were using window overlap, and I can't remember what the overlap was for this model, but there was certainly a window overlap as well. So I hope that's useful. So for every one of these windows, you're predicting a point on the shear stress space, and that's what's producing the blue line. So you make a prediction from that time window, you move that time window slightly forward in time, you make the next prediction, etc. And that overlap and the length of the window can vary, and you can do better or worse in terms of those predictions depending on that time window and the overlap. I hope that's useful.
Yeah, no, thank you very much. I think, I don't know if the initial question found that useful, but to me it was pretty clear. So maybe, I guess we're almost at the end of a question and answer session. There's a possibility, if you're still typing, I can still relay that. I was maybe, can I ask about the competition? That is also for scientists. Please. A very new approach to kind of put money on the table. I know companies do that quite a bit and kind of wait for the answers come. Did you learn something from the winning teams in terms of how to do that, or was it? I mean, you talked a little bit about that. Maybe we can expand a little.
Yeah. So the answer is yes. I mean, the winning teams. Let's see. I think all the winning teams were using deep learning, and we had used. To start out, we'd been using decision tree approaches because I'm not sure I mentioned this in the lecture, but we were using decision tree approaches because we wanted to determine exactly what the features of importance were. And you can't always do that with deep learning, but with decision tree approaches, you can. So that's why we started with simple models like random forest or XGBoost, and then moved to deep learning. In the competition, most people were using deep learning. And of course, with 4,500 competitors, it's hard to imagine the spectrum of approaches they were using, and the different, and for the parameters they were using, the hyperparameters, et cetera, for each of the models in the competition. But we did learn about some approaches people were using that we hadn't considered, and that was helpful. The interesting thing about a competition like this is that you can imagine that many of the competitors have no idea about the problem at hand. They don't necessarily know anything about geoscience, but they're good at machine learning. And Kaggle is attractive because, of course, you can make money as well. So there's a great motivation. But that's the beauty of the competition, and anybody interested in doing this that may be listening in today, I think it's a great approach to bringing people from outside the community to come in with new ideas and new approaches. And a number of the authors on that paper that we published in the Proceedings of National Academy were winners from the winning team, Team Zoo as they were called, from Germany. Actually, not just from Germany, the head of the team was from Germany. The team was a spectrum of people from many countries. So it's a really useful exercise is what we determined in trying to help advance the field. I'd like to see it again, but with earthquakes in Earth. And I think that's the longer term plan, that's what we would do.
Yeah, no, I think that will be great and interesting to see. So I think we've come to the end of a question and answer session. So the next program point, so to say, is the networking event on the neural network, which I guess most of our audience are already logged into. And I guess we as Paul as a speaker, me as a moderator will go to. So if you want to ask their questions on a more individual basis, I guess that will be okay. Is that all right, Paul?
That sounds great, Frederic. So I'll go find the site and sign in.
Okay, so I'll say goodbye.
Thank you.
I
Thank
see
you so
again
much.
at the other platform.
Okay, sounds great. Talk soon.
Okay, thanks everyone for listening in.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.